All right, so this is going to be the walkthrough for the homework assignment titled Continuity and Intermediate Value Theorem, or IVT. So first couple questions here, we're just being asked to verify the intermediate value theorem for some function f on a given interval from a to b. So for this one, we're trying to verify the intermediate value theorem for f of x equals x cubed plus 1, right, on the closed interval from -1 to 2. So the first thing you always have to do is you have to give a reason why this function is continuous on that interval. And so for our purposes here, this is a polynomial function. So we can say f of x is continuous on the interval from -1 to 2 because it is a polynomial. And that is always an acceptable reason for why something is continuous on any given interval. Polynomials are continuous for all real numbers. If you forget this step, you're going to end up losing points on your test. Right? You always have to state that it's continuous and give a reason. Right? So the second thing that we want to do is we want to find the value of f of -1. Right? So f of -1 is just -1 cubed plus 1, which is 0. And then we also want to find the value for f of 2. Right? F of 2 is 2 cubed plus 1, which is 9. And so what the intermediate value theorem says is, right, it says that by the intermediate value theorem, for every w that we could choose, and we don't have to use w, but for every w that's on the interval from 0 to 9, right, so between the y value at -1 and the y value at 2, so for every w we choose on 0 to 9, there exists a c value on the interval from -1 to 2 such that f of c is equal to w. And then we need to just prove that this statement is true, right? So this is what the intermediate value theorem says, but the proof of it comes from us actually starting with the inequality that we have w between 0 and 9 and turning that into an inequality with c between -1 and 2. So we're going to start off with the inequality 0 is less than w is less than 9. And note that we're talking about f of c equal to w. Well, f of c is just c cubed plus 1. So we're going to replace the w with c cubed plus 1. So we have 0 is less than c cubed plus 1 is less than 9. Now we'll just solve for c. And we'll subtract 1 from everything. So we get -1 is less than c cubed is less than 8. And then we'll cube root everything. Well, the cube root of -1 is -1. And the cube root of c cubed is c. And the cube root of 8 is 2. And that's exactly what we were trying to prove. That if we started with w between 0 and 9, we would end up with c on the open interval from -1 to 2. So that verifies that the intermediate value theorem is true for that function on that interval. All right, for our next one here, we're going to do the exact same thing, except we're going to use the interval -2 to -1, and we're looking at a different function, 2x minus x squared. So once again, f of x is certainly continuous on the interval from -2 to -1 because it is a polynomial. Okay. And then we want to find f of -2. Well, f of -2 is 2 times -2, or -4, minus -2 squared. And so that's just going to be -8. And we also want to find f of -1, which will be 2 times -1, or -2, minus -1 squared. Well, that's -2 minus 1, which is -3. So what the intermediate value theorem says is that for every w on the open interval between -8 and -3, there exists some c such that f of c is equal to w on the interval from -2 to -1. And so then we'll just go through and we'll prove that. So we're going to start with w between -8 and -3. And since we know that f of c is equal to w, and f of c is 2c minus c squared, it's just our function, we can replace the w with 2c minus c squared, and now we'll just solve. So what we'll do first, because this is a quadratic, which is a little more difficult to deal with than a cubic that doesn't have any other variables in it other than the variable being cubed, is we're going to want to get rid of the negative sign first. So we'll divide everything by -1, making this 8 is greater than a positive c squared minus a 2c is greater than a positive 3, right? And the inequality sign split because we divided everything by a -1. Well, then we're going to just complete the square, right? So we take the -2, right? That's the b value in our quadratic, and we divide it by 2, and then we square it. So -2 divided by 2 is -1, and when we square it, we get 1. So we're just going to add 1 to all of the pieces of our inequality. So now we have 9 is greater than the factorization of this, which is c minus 1 squared, is greater than 4. And so from there, now we'll just square root. Right, so we're going to get c minus 1 in the middle. But when I square root this, we have to remember that when we're dealing with these inequalities, we can kind of, at least in the context of the intermediate value theorem, we can pick either the positive or the negative square roots, or we can pick one positive and one negative square root, depending on the interval that we're trying to get. So the interval that we want in the end is the interval from -2 to -1. So if I square root and take the positive values, then I'm going to end up with 3 and a 2 that I then add 1 to, which is not going to give me -2 to -1. But if I take the negative square roots, -3 and -2 here, then when I add 1 to each of those, I will get -2 and -1. And we want to note that since we took the opposite of the square root, right, we took the negative square roots of these, then we need to flip our inequality signs here, right? And that'll happen. You'll always want to flip them when you square root the larger number. If the larger number, you take the negative square root of it, then that's going to cause us to need to flip those inequality signs. And so now when we add our 1, we just get -2 is less than c is less than -1, which is exactly what we were hoping to get. All right, for our next one here, we just want to prove that this function has an x-intercept on the interval from 0 to 6. And we're going to try to use the intermediate value theorem to show that. So first of all, we just want to state that f of x is continuous on 0 to 6. We have to do that if we're going to use the intermediate value theorem. And our reason is it's a polynomial. And then we want to find f of 0, which is pretty easy to find. F of 0 is just -40. And then we want to find f of 6. Well, f of 6 is a little bit more arithmetic. I'm not going to do all the arithmetic on there. But f of 6 comes out to be 1,400. And so we'll note that -40 is less than 0, and 1,400 is greater than 0, which tells us, by the intermediate value theorem, there exists some c on the open interval from 0 to 6 such that f of c is equal to 0, because 0 is between -40 and 1,400. Okay? And if I'd said, does this function equal 100, somewhere between 0 and 6, the answer would still be yes, because 100 is between -40 and 1,400. I could have said -20. Does it equal -20? Yeah. If I said, does it equal 1,500? Well, we can't guarantee that because 1,500 is not between -40 and 1,400. But this is all you need to do to guarantee that there's a root there. All right, here we have a piecewise function, right? F of x is x squared minus 4 over x minus 2 when x does not equal 2, and it's equal to a when x does equal 2. And we want to determine an a so that the function is continuous for all real numbers, right, on negative infinity to infinity. So what we need to do is we need to make the limit match up to the value of the function, right? So in order for a function to be continuous at 2, because that'd be the only place this thing might not be continuous at, the limit as x approaches 2 of f of x needs to equal f of 2, right? They both have to exist. That's the first 2 points of the definition of continuity at a point, right? The limit exists and the function exists. And then the third point is they have to equal each other. So we just need to find the limit as x approaches 2 of f of x. Well, that'd be the limit as x approaches 2. We can rewrite this as x plus 2 times x minus 2. And then we want to make that equal to f of 2, which is just a. And so, of course, we can cancel out these x minus 2's, and we get a limit as x approaches 2 of x plus 2 needs to equal a. Well, that limit is just 2 plus 2, which is 4. So as long as a is 4, this function will be continuous for all real numbers. This is the same basic type of problem, right? We just want to make it so that it matches up so that the limit as x approaches 0 of g of x is equal to g of 0. Right? Well, the limit as x approaches 0 of g of x is the limit as x approaches 0 of the sine of 4x over x. And g of 0 is just a. So this is a trig limit like we've dealt with in the past. We need to have a 4x in the denominator. So we'll just put a 4x down there. And we'll put a 4x, or just a 4 in the numerator. And so we can then pull this 4 out to the front, just like we did in some of those other homework assignments, giving us 4 times the limit as x approaches 0 of the sine of 4x over 4x needs to equal a. And of course, this limit is one we proved in class, right? This limit is just equal to 1. So we now have 4 times 1 is equal to a. So a is, just like the last problem, a ends up equaling 4. So this next one here is just a little bit more complicated, but it's the exact same idea. We want to find a and b so that this function is continuous for all real numbers. So the only place where it might not be continuous would be at the places where this matches up, -2 and 1. Right? And we can see that the function does equal -2 at 2x plus, like it equals, at -2 we use the 2x plus 1 piece of the function. And it does have a value at x equals 1. We use the natural log x piece of the function. So I just need to make the limits from the left and the right at -2 and 1 match up so that the limits exist at -2 and 1. Then those limits will just be equal to the actual value of the function. So we'll do the limit as x approaches -2 from the left of f of x. Well, that is just 2 times -2 plus 1, which is -3. And then we'll do the limit as x approaches -2 from the right of f of x, which when I plug in -2 to ax squared plus b, I get 4a plus b. And so for that limit as x approaches -2 to exist, I need 4a plus b to equal -3. So that's the first thing that we need to be true. And that's true for an infinite number of different possibilities of a and b. But we want the specific one that also works with the bottom part of our function. So we want to see when the limit as x approaches 1 from the left of f of x is equal to the limit as x approaches 1 from the right. Right? So as we do 1 from the left, we just get a plus b. And as we do the limit as x approaches 1 from the right of f of x, that's just the natural log of 1. Well, the natural log of 1 is 0. So for this part, we just need a plus b to equal 0. And so now what we can do is, since we have 4a plus b equals -3, and we have a plus b equals 0, we could solve this system of equations really in any number of ways. We could solve for a in this bottom one and substitute in. We could solve for b in the bottom one and substitute in. We could solve for b in the top one and substitute. We could solve for a in the top one, but that's kind of a pain. Or we could just subtract the top function minus the bottom function. And so, I don't know, I think I probably did a substitution in the answer key. But if I just subtract a plus b equals 0 from 4a plus b equals -3, the 4a minus the a is going to give me 3a. Okay? And the b minus the b will cancel out, right? We're able to just subtract those away. And -3 minus 0 is -3. So we just get a equals -1. And if a equals -1, well, since a plus b equals 0, then -1 plus b needs to equal 0, or b needs to equal 1. So if a is -1 and b is 1, then this function should be continuous for all real numbers. Okay, and we've used the definition of continuity, essentially saying that since this limit and this limit are equal to each other now, that means that the two-sided limit exists, and the same up here, the two-sided limit exists at -2. And so the limits exist, and we know the functions exist, and they're just evaluated as the same values as those limits are, right? Because we're just using the same function pieces. So the limits exist, the functions exist, and they're equal to each other. And that's it for the walkthrough for the continuity and intermediate value theorem homework assignment.